Hello friends, now we will go further in the phase diagram and come to the next type of phase diagram, which are one of the most important system, which is called eutectic phase diagram. So, in the last slide lecture, if you remember, we were discussing about isomorphous phase diagrams or isomorphous system, in which the two component have complete solubility. Okay, now we will see the systems where there is no complete solubility. Okay, and in that case, what changes takes place in the phase diagram. Okay, so binary eutectic phase diagram is a phase diagram between two components having complete solubility in liquid phase. So please keep in mind that they have the two component have complete solubility in liquid phase. In liquid phase, you can have all type of solutions, but when it comes to solid phase, then they start having limited solubility or partial solubility. And when this type of partial solubility happens, you also get an invariant reaction at eutectic point. Okay, we will see what do we mean by invariant reaction and what is a eutectic point. Okay. At eutectic point, the solidification behavior is akin to that of a pure material, as freezing takes place at constant temperature. So, if you again remember that when we said in a pure component, if you plot the time temperature profile, okay, the transformation will take place at constant temperature. This is what we discussed. Okay. So, for a single component, let us say I want to see in pure water. Okay. This is temperature, this is time. So, I will have cooling in the liquid phase, then the transformation at constant temperature, and then cooling in the solid phase. Okay. And that is why we call this as melting point or solidification point. In case of two component system, we said that the transformation happens at a temperature range. So, this is cooling in liquid phase, then the transformation from liquid to solid, then it is you have cooling in the solid phase. Okay. So, the transformation takes place over a temperature range if you have a more than one component. Suppose we say it is two components. Okay, this is one component. Okay, but in two component system also, where they show eutectic behavior or at eutectic point, okay, again the transformation will be like this, though we are having two component, but the transformation will be like this, and we will see that why this transformation will be like this. Okay. First, let me tell you what do we mean by eutectic. A eutectic reaction tells me that a liquid phase will transform into two solid phase simultaneously. So, in the binary phase diagram, okay, where you have partial solubility, okay, you sometime have this type of eutectic reactions where a liquid phase directly transform into two solids. Okay. And this type of one of the example of a eutectic system is a lead-tin phase diagram or lead-tin system. What is an invariant reaction? Point on the phase diagram at which degree of freedom is 0. So, why at eutectic point you get this type of profile? Because in this case the degree of freedom is 0. This is an invariant point. Invariant means you cannot change anything or it remains same, it remains constant. Okay, that is what we call as invariant. So, in this case it is invariant means that I cannot change anything in this, no variable can be changed because my degree of freedom is 0. Why degree of freedom is 0? We are talking about a two component system. So, my C is equal to 2, there are two components. Phases, as I told you, the eutectic reaction is like this, the liquid phase transform on cooling transform to two solids. Okay. So, there are three phases in equilibrium here: liquid, alpha and beta, two solids. Okay. So, my three phases are in equilibrium. Okay. And my relationship for the Gibbs phase rule is C minus P plus 1. Okay. Pressure we are taking as constant. So, it will be 2 minus 3 plus 1, 2 minus 3 will be minus 1, minus 1 plus 1 0. So, you have a degree of freedom as 0. That is why at eutectic point you will get a temperature profile like this. Okay. And that is a invariant reaction, means there is no degree of freedom, the degree of freedom is 0. So, this is a typical eutectic phase diagram. This is drawn schematically. So, it may not be possible that maybe some system has something like this. I have drawn it. So, you can again see that you have 100% A at one end, 100% B at the other end, and the composition of B is increasing from left to right. Okay. In the isomorphous it was very simple, you had liquid, you have liquid plus solid, and then you have solid phase. Here you can see that it is more complicated now. In the liquid phase you can see that there are no phase boundaries. That means there is a complete solubility of A in B in the liquid phase. Okay. Now, there is a very important point here which is shown by E, it is called eutectic point. Okay. So, you can see that at this point, above that you have a liquid phase, below that you have two phases alpha and beta. Please remember, there will always be a two phase region between the two single phase region. So, as you can see at the left hand corner you have a single phase alpha, at the right hand corner you have the single phase beta. So, any phase diagram between these two single phase will have a two phase region which will be alpha plus beta. Similarly, you have alpha here at the left corner, liquid phase above. So, any this phase region, okay, between these two single phases will have two phase region which will be alpha plus liquid in this case and beta plus liquid in this case. Okay. So, let me draw it and show you all these things on the board. Okay. So, a eutectic phase diagram will look like this. Maybe take something else here. Okay, better than the previous one. So, if there will be one single phase here, okay, then there will be constant temperature line, then there will be another phase line like this, there may be something like this. Okay. So, this is 100% A, this is 100% B. As I told you, at 100% A, this point from which the solid phase is going into liquid phase, you will have melting point of A, and here you will have melting point of B. Okay. Now, some more things we can quickly plot. This is my liquid phase, okay, complete solubility of A and B. This is my solid phase, but there are two new things coming up. Now, you have two different solid phases, one which is I am going to call as alpha and another one which is I am going to call beta. What is alpha? B soluble in A. So, A is solvent, B is solute. Okay. You have more of A, less of B. Okay. So, the alpha phase, now I will call it as phase. So, alpha phase solid solution of B in A. So, B is solute, A is solvent. Beta phase is solid solution of A in B. So, A is solute, B is solvent, okay, which comes here. Now, as I told you, between any two single phase there will be always a two phase region. So, if this is alpha phase, this is liquid phase, there always going to be a alpha plus liquid phase in between. This beta phase, this liquid phase, two phase region will be here, which will be beta plus liquid, okay. This alpha phase, this beta phase, region between them will be alpha plus beta, okay. And at this point you can see that liquid phase, suppose I take a composition exactly of eutectic, okay, liquid transform into two solids alpha and beta, okay. So, here the liquid is transforming into two solids alpha and beta. So, that is the eutectic reaction, invariant reaction, where the degree of freedom is going to be 0. Now, which we can see that this will be my liquidous line between liquid and liquid plus solid. This will also be liquidous line, liquid between liquid and to solid. Another line which is or boundary which is going to come here, which we saw earlier, is called solvus boundary or solvus line. This gives me the solid solubility of B in A, okay. So, as you can see that at different temperature the solubilities are different. Okay, as I am increasing the temperature, the solubility of B in A is increasing. Now, at higher temperature I can have more solubility of B in A, and the maximum solubility will be given by this point, that this is the maximum I can have solubility of B in A, I cannot have more than this. Similarly, this is the maximum solubility of A in B, I cannot have more than this, okay. And this is a exponential dependence, again a temperature dependence, okay, that how the solubility of B in A is increasing as a function of temperature. Now, in this particular slide you can see that there are different points are marked here, okay, and at each point we are giving you a list that what different phases will be present, what will be the composition of each phase, and what will be the degree of freedom at that point, okay. So, if you see at point P, you have only one phase, liquid phase. Composition of that phase Cl will be weight percent of B in A, which is the overall composition, okay. You can say Cl will be equal to C naught at this point, and the degree of freedom will be 2, okay, because you have two component, you have one phase, okay. So, degree of freedom will be 2. So, I can change the temperature as well as the composition in the liquid phase without, so I have 2 degree of freedom, both can be changed, okay. At point Q, you have two phases present, alpha and liquid. Composition of each phase, alpha phase has a composition C alpha in alpha plus liquid, and composition of liquid is Cl in alpha plus liquid, okay. Again, as we did earlier, that I can have a tie line. Suppose this is my point Q, this is the overall composition C naught, and if I draw a tie line like this, this will give me the composition of C alpha in alpha plus liquid, this will give me composition of C liquid in alpha plus liquid, and total C here composition is Cl is equal to C naught, the overall composition, okay. The degree of freedom here is 1, okay. Either I can change temperature or I can change the composition at a particular location, okay. Point R, that is in alpha phase, okay. You have one single phase alpha, the composition of that phase will be equal to C alpha, in alpha phase, okay, and degree of freedom will be 2. At point E, there are 3 phases in equilibrium, liquid, alpha and beta. The liquid has the composition of Cl, alpha has the composition given by point M. Okay, so just below the eutectic point we can find out. So, this is the composition Cl being divided into alpha and beta. So, alpha will be having this composition and beta will have this composition. So, maximum solubility of B in A, maximum solubility of A in B, okay, which is in this particular slide is given by point M and point N. At point S, you have again 2 phase alpha plus beta, okay, and the composition C alpha plus beta in alpha plus beta and C beta in alpha plus beta, and degree of freedom is again 1. Okay, so, this is the complete information of this particular phase diagram at different points. What are the different phases present, what are the composition of these different phases which are present, and what is the degree of freedom at that particular point. Okay. Again, in more ways the same information is shown, okay, in terms of percentage here now. Okay. So, for example, you have a overall composition C naught of 20%, okay, given by the point O. If at 2 phase region I want to find out what is the composition of alpha, that will be given by C alpha, for example, here is 10%. At point N, it will be composition of liquid, which is given by 40% B, okay. And now I can also find out that what will be the fraction of each of these phase. For example, at point for overall composition of 20% at point O, okay, I want to know at a temperature which relates to the point O, which is given by T1 here. I want to know what will be the fraction of alpha phase and what will be the fraction of liquid phase. So, let us do one calculation here. So, according to that diagram, we are saying that overall C naught is equal to 20% B, okay, and from here we are saying that the C alpha has the composition 10% B and C liquid has composition 40% B, okay. Now, I want to find out suppose these are in weight fraction, what will be the weight fraction of alpha phase, for example, weight percentage of alpha phase, okay. So, again we will use the lever rule here, okay. So, this is my lever arm, okay, fulcrum is at 20% B and this is at this at 10%, this is at 40%, okay. So, I have the compositions, okay. So, I will use this composition. So, weight percent of alpha phase will be given by this arm length. So, this will be CL minus C naught divided by CL minus CS, okay. If I put all these values, CL will be 40 minus C naught is 20 divided by 40 minus 10. So, this will be equal to 20 by 30, that is 2 by 3. If I want to know weight percent of liquid phase, then it will be this arm length, okay. So, 20 minus 10 divided by 40 minus 10, that will be equal to 10 upon 30, that is equal to 1 by 3. Now, if you remember, I told you that I can get weight percent of liquid phase just by subtracting what if I have got 2 by 3 in as weight percent of alpha phase. If I subtract this out of 1, I will get the weight percent of liquid phase, okay. So, if it is in percentage, I say percentage, if it is in fraction, I say weight fraction of liquid phase. So, right now it is in fraction, I can say weight fraction of liquid phase, or weight fraction of alpha phase. Okay. So, this is how you can calculate the different compositions and different weight fractions. Okay. Some other also are shown here. For example, if Eutectic has a 69% overall composition, you can find out that what will be the fraction of alpha phase in this and what will be the fraction of beta phase. So, the overall Eutectic composition is given by 69%. I want to know what will be the composition of alpha phase. So, that is coming as C E alpha as 11%, at F it is coming C E beta as 88%. Okay. And so, you can find out that what will be the fraction of alpha phase and what will be the fraction of beta phase in a Eutectic so when Eutectic reaction is going to take place. Okay. And with that I say thank you. Okay, we will stop this lecture here itself, and then we will go to the cooling and how the microstructures evolve during the solidification in different systems. Thank you.